you have to take senior design and fall into the second. But tonight, what practice is technically classes on just technically
Okay. Welcome everybody. Welcome everybody to class.
Sorry.
Is it working? Okay, well now I'll try. All right, can you hear me now? All right, sorry about that. Welcome everybody to class. That is now really loud. Let's calm that down a little bit. Okay, is that better? No, that's worse. Okay, happy medium? No, not happy medium. Happier medium? Okay, great. Welcome everybody to session 2. I hope you're doing okay. In this session, we're going to cover or review some concepts from statics. Okay, so sometimes folks are like, well, let's have a little like mini quiz refresher, and sometimes we're like, well, let's do a little review. And so in this case, we're going to do a little bit of a review, but there are questions, of course, on the homework on this topic. Okay? And so I just like to point out a few things before you all get started. And of course, there's still time to work on a question or two from the previous assignment from session 1. Okay, so after we do kind of a little bit of a introductory hoopty-doopty here, then we'll have a problem-solving question, and Praj and I can go around and answer questions in session 1 or session 2. Okay. Any administrative questions though before we get going? All right, great. So there are kind of going to be 3 types of structures that we look at in this class. We're going to be looking at Oh, it is supposed to be showing something, yes. Okay, sorry about that. Give me 1 second here. All right. Coming. Everything's coming. All right. So, here we go. All right, we're in session 2. All right, and we're talking about equilibrium. So there are 3 basic structures that we're going to be focusing on in this class: spars, shafts, and beams. Okay. Now, we can say in this session of notes, there's also discussion of trusses. And yes, we will discuss them a little bit. They are kind of an exaggerated, well, not exaggerated, but an amplified version of bars. Okay? Because if you recall from statics, trusses are formed of what are called 2-force members. So at the pins where you put them together into the truss, they don't have any moments being applied to them. So we don't think of them as beams. Right? And for this assignment, session 2 assignment, you don't have a problem on trusses, but later on, I think we're in session 4, so not even the next session, but on session 4, there will be some questions on trusses. So you can go back and look at those notes. Keep them handy. For bars, essentially what we're talking about is a circular or rectangular member that has some type of force acting along it. Okay? And if you look at this bar, you immediately say, okay, it's in equilibrium because this force and this force are the same. And we kind of take that for granted. Now, if I cut this bar in half, okay, what is the magnitude of that force inside? It's the same, right? This thing's got to be in equilibrium, right? So you remember taking slices, and this is our first review of what we call method of sections. Right? So this is method of sections. Yes, it can't get much more basic than this. Okay? I mean, I guess I could write, and I probably should write, F equals ma, and we're saying acceleration is equal to 0 here. Okay, but this is very core. Now, for these given directions that we've given here, okay, if F is greater than 0, is this bar in tension or compression? Tension, right? Okay, thank you for raising your hand. Whatever, we can do however we want to do it. Okay, but that's great, yes. It's in tension, right? And that's pretty simple to see in terms of I've got a force on either end and I'm pulling it apart. Now, if F were negative, right, if F is less than 0, then you know where this is going. This is in compression, right? Now, let's take a careful look, though, at this green internal F. This is often a little bit confusing for people. Not everyone, but for some. Okay? Now, what did I do? I just drew the bottom half of the bar. Okay? And if F were negative, those green forces, all right, these ones here and here, I'm sorry if the color is hard to read, these ones here and here, okay, they're in opposite directions. So, does that confuse anyone? Maybe not. Maybe everything's hunky-dory, right? Because you're like, okay, well, I remember that since this F is coming out of this bottom face, then this F that's coming out of this internal face, even though it's going the opposite direction of this F, everything, if F is positive, everything's still in tension. Okay? And if you remember that, you're in good shape. Okay? If F is less than 0, then everything's in compression. Everything's flipped. So what we have here when we do method of sections for normal loading on a bar, we actually have a convention. Not where we get together, but we have a nomenclature, we have kind of a convention. And the typical of that convention, you probably are more thinking about it in terms of what we drew last semester a lot of times, right, in terms of a beam, okay, is that if I have some force coming out of this face, and I have some force coming out of that face, they're equal and opposite, and if it's coming out of the face, it's in tension when I take the internal slice, and when it's coming into the face, it's in compression. Okay. Now, you'll see in the notes that we do some things where we put multiple external loads on the system. Okay? And we put multiple external loads on the system, and we still have to sum up all those loads. Okay? And then maybe we take a slice somewhere. And you'll see this on the assignment. Okay? Remember, when you're doing static equilibrium, what's the first thing that you do? You look at the external loads and you make sure that all of them are balanced. Right? First external equilibrium, then after you've got as much of the external equilibrium taken care of as you you can, and later in this course, we'll cover some things where external equilibrium is not trivial because you have what are called indeterminate systems, where you have a system that's over-constrained, it has too many external constraints on it. Okay? And so then you have to know something about how the constitutive, how the deformation is affecting the system. Okay? But very simple concept, just want to put it out there. Shafts. Okay? Definitely, for me at least, a little more confusing. Okay? So often we'll draw a shaft, something like this. Okay? And when I put the torque, the external torque that's acting on the system, okay, I'm going to think a little bit about using the right-hand rule to make sure that that torque is either positive or negative with the coordinate system I'm defining. Okay. So let's just say if this were in the z direction, and I said this was plus z, you could say it's plus x, whatever you want to say. Okay. Let's do this a little bit bigger. And let's say that's the A end. Okay? Is this torque that I defined with respect to plus z positive or negative? Positive, yes. Right? We're using the right-hand rule. Okay? And so similarly, just like we said, we often define the open face as having a positive vector coming out of it when we define the direction of the force. This is similarly true here, except now we're using the right-hand rule and we're thinking about torque. Now, the way I've drawn this, is this shaft in equilibrium? No, not yet, right? So what do I need to do? I need to make sure that I have a TB, okay, on the other side. And if I were to think about having something that's positive coming out of this, right? Which is a little bit, this is not really a plus z, this is kind of a little bit shaky, right? It would be negative if that's plus z, but it can't really be plus z because that's z, right? I mean, maybe this is z1 and z2, okay? All right, and then, that's not the same coordinate system. The point is that we have to be very careful about this direction, all right? So TB, if I'm using the plus z1, it would be in the negative direction, right? Okay, because it's going negative, right-hand rule. But if I'm using this plus z2 in that direction, then it's going to be positive. So often, now that's just for the external equilibrium. Okay? If I take this shaft and I cut it, oops, that's too smart for me. Okay. Okay. Okay, plus z. This is where it gets a little bit dicey. And so sometimes what we'll do, okay, is we will go ahead and we'll actually go ahead, we'll say we're going to define some positive coming out, okay, and maybe we call it plus z internal, all right, like that. And which direction would we want to make this internal, t internal? Well, if we want it to be positive, okay, and counteract TA, all right, we're going to draw in that direction. Okay, so that puts this system in equilibrium, and T internal is a positive torque according to plus Z internal. Yes.
Why is the other direction also positive?
Right. So what you often do, just like we said here, we say this is a face. I'm going to make a vector. I'm going to call the positive direction coming out of the face, right? So like when you're calculating fluxes and stuff in multivariable calculus or whatever, right? You often say, okay, if it's coming out, it's positive. With the torques, it's a little less important whether it's positive or negative, because we don't but it's still very important to keep things straight. And as you'll see, if you look in the notes, I talk about this a little bit. I have trouble keeping track of which, is it a positive shear stress or is it a negative shear stress? And the positive shear stress, okay, we're getting a little bit ahead of ourselves, okay? But we're going to have compressive stresses, tensile stresses for bars. We're going to have shear stresses for shafts, okay, under torsion. Twisting results in shear, okay? And the direction, whether it's a positive or negative shear stress, is going to depend on which coordinate axis you're using, okay? So I just want you to be aware of this right now, okay, as we're doing things. Now, what about beams? So you remember if you had a beam, and often they were cantilevered, right? But they don't have to be cantilevered. We had to think very carefully about what we did with the transverse loading. In other words, loading that was not along, right? But going across. Okay, and we'll talk a lot about transverse stuff in this class. Okay, so if I have this system, and this is maybe something you're like, I've seen this a lot, right? When we do method of sections, we had some conventions that we keep track of, okay, and so what the first time I was teaching this class, I was confused. I was like, wait, and I still get confused. Okay, this is not the way that. Something's weird. Something's backwards, and it's true because the textbook I used a different convention than the textbook, or than the Hibbler's textbook. Okay, so the convention we're going to use is something. Let's see if I can get it right because I don't have my notes in front of me, so I always have to look. All right, but if I took an internal slice here, okay, and if we're looking at the internal shear force and the internal bending moment, right, that's positive, the way it's defined, if we're opening to the right, and then this is positive, like this. Okay. All right, now, maybe I should go back and look at this problem a little bit. And then let me do the other one, right? So if I open to the left, okay, then this shear force is positive upward, and this moment is the opposite direction. Now, notice V and M, right? Assuming that let's just say I'm halfway across the beam, okay? So let's say that this cut is, this is L. I guess I can draw it. Right, and this now we're going to say we have some coordinate system X, and let's just say that we're at X equals L over 2, right, in both cases. So we would have, look, this is confusing. V and V are in opposite directions, okay, but they're the same. Okay, they are identical in magnitude here with this convention. Okay. And let's just go a little bit further. So in this case, right, we have that V and F, right? So if we do forces, right? So we do static equilibrium. On forces, okay? often we pick the positive direction for these to be up, okay, in terms of a vector direction. So, if we're doing this, I'd say we have, whoops, I don't know what I'm doing, but we have v minus f equals 0, so v equals f, right? What is m here? Okay, that's a little bit tricky, right? We have to be a little bit careful. So here, we're going like this, and we said this is at x equals L over 2. Okay. I gotta pick a location. Usually I pick a location when I do this that's right here, so I can not worry about v, what it is, right? But if I pick that location, right, then I've got, and then normally, right, I gotta pick a direction as well. Normally I'd say coming out of the board at me is positive z, we'll call it, or torque direction, right? So if I've got that x times f, is that if z is that a positive or negative torque? The way I've defined x. If I'm doing it at this interface, is that a positive or a negative torque? xf. Assuming x is going from the right and I got a positive direction, is that L over 2? Huh? Say, I can't hear it. Okay. Let's try the other one. Okay. So here, right, this torque is acting downward. It's right-handed rolling it into the board, right, into the page.
You're talking about the one on the right or the one on the left?
I'm talking about the one on the right, xf. Okay? This has got to be a negative. All right? If I'm saying that positive z, okay? If positive z is coming out of the page, all right? And I'm glad you said something. I'm glad you gave an answer. I'm sorry. I'm glad you said something, all right? This is why we're doing this, because I think this is often confusing for folks. This is minus xf, and is the m then, is m positive or negative?
Negative.
Yes, all right? We're getting there, right? Okay, so m is equal to minus xf.
Sorry, how do you get x up?
This is x is the distance from, here, maybe I'll show here so everyone can see. X is the distance from here to here, right? As I, remember you take the slice at different spots, okay? And so as I move that, I got it right. This is the x, okay? That's the distance, all right?
Would they just not rotate it?
Well, yes, it better not rotate. I agree, it's static. Nonetheless, we still need to figure out what the moment or what the torque is on this system, okay? Because it has to be in equilibrium. Otherwise, it's going to be accelerating. Okay? And when I say in this case, if it's accelerating, it's actually angular acceleration. So this system, all right, should give us the same result as we have here. Okay, but we have to do something a little bit differently. We have to make sure we solve for the external equilibrium first on this one, right? So first, right, we first do the two steps. Our first external equilibrium. And I kind of cheated because I said, I don't want to do external equilibrium. I just want to, I have external equilibrium, okay? If I just take a slice there, then I don't have to figure out what the reaction was happening at the wall. Okay? But if I look at this one first, if I do this case, then I have to figure out what in the world is happening on the wall. So if I do first external equilibrium, I come back all the way to the left. Okay, and what do? Now it does not matter what I use for convention. Remember this. I'm going to put reaction force and reaction moment from the wall on the beam, but there's no convention rule. The convention rules apply to internal. Okay, they apply to the internal force. Yes, go ahead. This is x times f.
Oh, I see.
Yes. All right. Is that so? This is a distance. And this is a force. So if this force is in newtons, then newtons times, and if x is in meters, then this is a newton meter. And that is going to be. So what am I doing here? I'm really doing sum of the moments at a location equals 0. Okay, that's what I've done there. Thank you for the clarifying question. Okay, so back here, I like things to be positive. So what we were saying a second ago is, I don't care about the convention. I just want to put forces and moments from a reaction on the beam in the orientation that causes me the least amount of headache. Okay? So to do that, what do? I say, well, I got a sense that this force is going to be kind of trying to make the beam go this direction, and maybe I gotta resist that force. So I'm going to put a moment I'll call ML because it's on the left side. All right. See that? Because if this were a pin, what would happen if I put that force there? It would just go whoop. All right. And actually, if this force stayed orthogonal, all right, it would just spin it around and it would just start accelerating. It'd be very exciting. Okay. But it's not a statics problem. That's a dynamics problem. All right. So there has to be, to your question, it has to be a moment to kind of make sure that this does stay statically placed. All right. So okay. So which direction should I pick for the FL? I'm going to pick vertical. Right. Convention does not matter. Convention does not matter. When I say this. Convention does not matter here. Convention does not matter here. Okay? It matters internally. I'm trying to make my life easy because I want FL and ML to be positive. Right? So when I do the equilibrium here, what do I have? I have, well, FL just has to be equal to F. Right? I mean, I could go through it and say FL minus F equals 0. Right? But FL has to be equal to F. Similarly, all right, ML is resisting. And, it's important to realize that this is the constraint. These are the moment and the force on the beam applied from the constraint. If I wanted to look at what's happening at the wall, right, I would flip things. What is the beam acting on the wall, right? I always get confused on this, right? For every action, there's an equal and opposite reaction. Okay, and from one body acting on another body. Okay, so anyway, so ML is just FL. Okay, so I've done that, and now if I go back to this problem, everything's getting a little bit of messy. Let's see, what can I think I'm allowed to do this? It's one. Okay. Let's break down this problem up here. Okay. So now I've got the beam cut there. I've got F, and I've got FL right there. Okay. And I've got my convention here internally, and I've got my moment here. Okay. And so, and I've got a coordinate system where X is going that direction. Okay. Let me make that a little bit less messy. Okay. So now, if I look at this, I'm going to say V is the easy one. All right. So V, right? V is just got to be equal to F from this. All right. So V is going to be equal to F. The harder one is, okay, I got to figure out what M is equal to. So let's pick this location. I'm going to say the sum of the moments, okay, and we're going to say at right side is going to be equal to 0. I could pick the left side if I wanted to. All right, it doesn't matter, but we'll say at the right side here. Okay, that the sum of those moments has to equal to 0. In that case, when I do it there, V is contributing 0 moment, all right, which makes my life a little bit happier. In this case, is M a positive moment or a negative moment?
Positive.
Yes, thank you. All right, so we'll say M plus, well, actually, let's say plus M, really. It doesn't really matter, I guess. And then is FL positive or negative?
Positive.
Also positive, right? Okay. All right. So that's how you solve for the internal force and moment. And what do you know? Okay. Hold on. No. I did a mistaker. What did I do, guys? I did a mistaker. I forgot something.
The moment of F.
Yeah, I gotta get the moment of F. Is F contributing a positive or negative moment?
It's going to be negative.
It's gonna be negative. Thank you. Good. All right, now we have M is equal to Fx, okay, minus Fl. All right, now you're thinking, wait a second. You said that V and M are going to be the same if I'm at x equals L over 2. But this expression is different than this expression. What's going on? Well, what is going on? Well, first, the V equals F and the V equals F, those check out, right? Those are nice. Well, I got to plug in L over 2, right? So at L over 2, and remember, they're different. X is coming from the right side, so later in the class, we'll call this like x2, and we'll call this one like x1, all right, to keep track of things. But at L over 2, okay, what we're going to say is that M is equal to minus L over 2 times F, right? And then over here, at x equals L over 2, right, we have FL over 2 minus FL. This is also equal to minus FL over 2. Okay? So everything lines up quite nicely when you get to the middle. And once again, remember how you're like, oh, this is so simple back here. I have an F coming out. I know if it's in tension or compression. No problem. This is less intuitive, as was the shaft one. Because V is going down in this if I leave the right side open. But V is going up if I leave the left side open, right? But they're describing, they have the same magnitude, and they're describing the same state of internal force. Okay. Any questions on this? All right. Yes.
You put FX to that one.
I'm sorry, say that again?
You put the FX to that formula, right?
Fx, yeah, I put x equals L over 2 into X.
Yeah, for the one below.
Which one?
Right.
This one?
Formula? Yeah.
This one? Yeah.
Above that.
This one?
Yep, the fx. Like, what does that mean?
This is f times x. Right? So this is, huh?
It's just a new moment.
It's describing the moment from this force F, right? Acting a distance x from this point, because we're summing the moments at the right side. So the moment arm, the length of the arm is x, and the force is F. And that's the moment that's being applied. Okay? Yes?
I don't want to take up too much time, so if I'm still confused on this, is there like a video you recommend?
Yeah. I mean, you have my video. Just look at Jeff Hansen's stuff on statics. This is, how do I put this? You did this, I think, a bunch of times last semester. Okay? So, I would go back and look at your statics notes, okay? And there are videos on this. You can do videos on this too. Just be careful, the convention. These purple ones are the conventions, okay? Yes?
Yeah, I also feel like I need a little bit of a refresher.
Okay, well that's what I was trying to do here. That's what I'm trying to do here. This is the refresher, guys.
Okay, I don't know, I feel like it was strangely the final. Yeah, I don't know.
Okay. I will, so at the bottom, if you want to get the textbook, you can look there. Yeah, I can attempt to answer questions individually. I think we've got to talk about this during office hours. This is definitely, yeah, I think that's the place to talk about it. Okay, if you want to have a dialogue about it. Okay? All right. So, go ahead, all right, and get ready for attendance. It's a little break. You can stand up, party, do whatever you want. Okay, and while we have, let's see, well, what am I trying to say? Okay, we've got about 40 minutes or so left, okay, and Raj and I would be happy to kind of answer questions. Yes, Owen. No, what's up, Owen?
I was just trying to get, like, the TA to help me sign.
Oh, okay, all right. Yeah, okay, so hold on. Okay, so just, yes. We can go around, and if there's a common question, right, we can come back to the board, and we can kind of address some of those common questions. I have a question for you. I posted in the group this morning. I thought I posted in the group this morning.
You didn't give us the GroupMe link yesterday, or 2 days ago. You just said GroupMe and then 2 people.
Fun stuff.
It's on Canvas. Yeah, in the announcements, there's only one announcement, and it's right in there, and it's also on the skill list. Okay? So, did my post get into the GroupMe? It did? Okay, because GroupMe does funny things, especially when they're like a lot of. It's great. I'm really happy to see that. Right? But I look back because I can't even find my own post on my phone. Okay, so I hope for question 10 that was a little bit helpful, all right? But if not, we'll go through, and I hope for the other question on power, I hope that post is also helpful, okay? But if not, we can go through. Just a note on the group meeting, all right? Let's keep it PG, all right, in the group meeting, all right? I know you can delete your messages, right? Just let's keep it PG, all right, and respectful. Think of it, if you were to send these types of messages to your future boss, would you have a job the next day? All right? That's the type of environment we want. I want people to help each other out. All right? I'm just saying the tone matters. Okay? All right, let's, yes. Okay, attendance should go, there should be, I'll pull that up in a sec. We did this yesterday, and I had trouble yesterday. Hopefully it'll work.
Probably was the end of the semester. I only have a speaking.
Yeah, so just 1 second.
And I don't start. I don't understand because I thought.
Did the attendance not show up for you guys? It did show up. It should show up under here for 9-7. I don't know why. Canvas was giving me some issues, okay, but it should show up. Or maybe I'll do it in the student view. Okay, I don't know why it's not showing up here, but it should show up here for 9-7. All right? Good. All right, we'll go around and we'll answer some questions. Okay. Okay, so there's a question about question 10, session 1, all right? Okay? The approach is to think about ratios, right? So we have a force that we want, a new force. We have an old force that we had that was supportable by this beam. Okay? And this is for the cantilevered beam. Okay? If you have so Praj is here too if you have other questions, okay? So if I am interested in figuring out what the new force can be, it's about ratios, right? So if the length of the beam increases, can I support more or less force? I'm asking you. If I change the length of the beam, does it support more or less force? Right. Okay. So it goes down. If L new increases, right? Then it goes down. If I increase the width, the top of the beam, the width, does it go up or down? It supports more. If I increase the thickness more, right? And it goes with a square. That's it. And then you've got to know that 1 pound is equal to 4.45 meters. Okay. All right, other questions?
Yeah, so I take it.
Stuff is due Tuesday. You in the class?
Yeah.
Thank you.
Good luck. Yeah.
Approach this problem. I thought it was about the same as the first question, where you cut it, but it doesn't. Like when I do it and add up one side, it doesn't. It's not the answer.
I'm confused. So did you calculate out what FD is?
Yes,
Okay.
and then I just put an FD as the answer, or do I have to just?
Well, what was the sign on FD?
It is positive.
Minus 83 plus 195 plus 123. FD is not positive.
Wait, can I not do that with just ABC? Can I do ABC but the?
You got this is the equation for equilibrium, right?
No, I get that, but I'm saying like, would I be able to do the other side and not just do D?
You need to figure out what D is.
I have to figure out.
Right. You have because I didn't give you D, right? So you have no choice. You have to figure out what D is, and then you're right that FCD will equal FCD.
Okay.
Got it? Okay.
Can you
Yes.
fill the attendance real quick?
Yeah. Hold on. Except, actually, there's an issue with the attendance for some reason.
Yeah, I still haven't been able to submit it.
You haven't been able to submit it?
I think I wasn't in the quizzes section the other time.
Yeah.
It was like quizzes and then like it was at the top.
Let me resolve this, and then you guys, I'll put it up again. All right. Just give me a second here.
So I was doing one of the problems from the like homework. So it gives you A, B, and C, and then it has D going also like away, going out, looking like it'll be in tension. But
Yeah.
if you do the math, like the D can't be in this direction. So it's just a like
It's
kind
a
of
negative.
A so it's a negative, but it like the force would actually be going in this direction. Okay, that's what I
Yeah.
was
So that's what
confused
you're getting
about.
at. So that's what we're getting at.
Because it was the same for the moments for one of the shaft problems. So okay, thank you.
All right. Yes.
So I'm just wanting to ask, like, this is my second time taking your class, and I'm just wondering.
Let's talk after class because it's recording right now.
Okay.
Let's talk after class. Okay, what's up? Oh, you guys are still waiting, right? You're not on campus?
No, I'm on the class campus.
Say that again. You're not on campus.
Yeah, no, I'm not in the class, like, on campus.
Okay, so you want to be in the class.
Yeah.
So your
But
question is,
I'm
can I?
I'm registered for the class, I'm just not on the class. Like, I don't have access to it on campus.
This is recording, so let me just mute this for a second.
Shouldn't be. You are hanging so much.
Okay.
He says the
All
same
right,
thing.
so for those having issues with
That's just gonna be really
when you go
awkward.
into quizzes, I'm not quite sure why
If
Canvas is not. I must have done something wrong.
It's
right?
not consistent.
User is
right?
wrong, but
I
it-
haven't.
the attendance is in their quizzes.
Professor does not have.
All right. Yes. Question.
You're doing great.
Just two? Yeah.
It's not.
Yes.
Wait, so okay, I'll look at the lecture slides. Thank you
I mean,
much.
this is it.
No,
I
no.
already did
Your name
this, and this was it.
Okay, got it. Thank you.
Yes.
So I was looking at that same shaft problem where it's like A, B, and C. You have TA, TB, TC.
Yes.
TA is like in this direction, TB or no, TA is in this direction, TB is in this direction. And then TC is drawn in the same direction as TB, but it ends up it can't be in the same direction because TB is greater than TA, right?
So it's
Like, and then like because when I found the internal limit, it seemed like it was supposed to be equal to TC. Between like it was between B and C. I wish I had the problem up.
yeah. It is. So it depends on which way you take the slice.
Okay.
All
Yeah.
right.
So
So
it's
you're
slice
absolutely right.
here. Yeah.
The TBC is going to be equal to TC.
Okay.
Right, but when you take that slice, right, you're going to have whatever the interface is. You're going to define TBC as positive about that interface, about
Okay.
that the vector coming
Okay.
out of the face.
Yeah. Okay.
Okay.
So then TC would be negative in that case.
Well, TBC, okay, is going to be it's going to be actually equal to TC.
Yeah. Oh, so they're going to be they're going to be exactly the same sign. Okay. That's
Right,
that's-
because it's coming out, because you have the vector coming out of the face.
Right. Yeah.
It's like that.
Okay.
Okay. Your name is?
Ethan.
Okay, good. Yes.
So, I just have a quick question in regards to like more statics review. What you would suggest, just because my previous education where I learned statics from, for back better terms, it's bad.
Okay.
It wasn't from here. It was
Okay.
just
That's-
I don't have a lot of knowledge on that.
Okay.
So I was just wondering some of your resources that you would suggest in regards to that.
Yeah, so there's some resources. There are some resources on the web page.
I was checking out like Jeff Hansen
Yeah.
and that type of stuff. I
Yeah.
was just
So,
wondering if
I mean, so for today, so like, if we go back, I mean, I don't expect you to review an entire course. Okay, for this, that's not practical. Hopefully, what we talked about with the bars, that was like kind of familiar. The shafts, the nomenclature, may be a little bit unfamiliar. The beams should be familiar, but I understand that it's a complicated thing. So I would go back, if you have Hiller's book, you can look at that. That's a pretty good resource, okay, for statics, at least using the conventions that we're using. And then, yeah, I mean, looking at Hansen or beams, there are going to be some videos.
Yeah, I know that. So I'm gonna transfer from a county college, and I have a couple of my friends that are like up there that are kind of looking at this. And we're like, we just really check this out at all. It was mostly like free body diagrams and things like that. Very
That's what this
rudimentary
is.
stuff. Yeah.
That's what
So
this is.
it just more extended based on that?
I think maybe it went a little fast
Okay.
if for folks that don't, whatever, the background is different, right? How do I say this? Go back into statics and find this exact beam.
Okay.
Right? Or go online. Find this exact beam. Just Google cantilever beam internal force.
Right.
Right? And what you want to be able to, and internal force, internal moment. Right? And what you want to be able to do, at least by the end of today, right, is be able to figure out, okay, that's internal shear force, that's internal moment.
Yeah.
Okay? And that's like a start. Right? So I wouldn't like you go back everywhere. It's like
all
just
the way through
look.
statics.
Right. It's like look at
For
each
this.
look for the examples that we've done, and you'll find them in stacks.
Okay, awesome.
All right.
Thank you.
Hi, my name is Jake. I was just wondering if you posted what time your office hours are going to be.
Yeah, they're on the syllabus.
Okay.
So on the syllabus, actually it's online, and and it's also on. So if you go to course, and it may be a little bit confusing, but there are. Oh, I didn't post it. Okay, it's definitely in Canvas though. So if you go over to Canvas, I need to post it. And you go to the announcement right here. Okay. And if you click on syllabus, this is when office hours are.
I think I have classes then. Do you make them by appointment?
So you can't make any of these Monday, Wednesday, Friday.
Maybe Friday. I'm trying to like switch a class from that time, but
Okay.
like right now
So
I do have a
let's
class.
Friday's tomorrow, right?
Okay.
So let's see if you can. If we
Oh
can
no,
chat.
I don't mean I need help yet. I'm just saying like.
Oh, okay, yeah. I mean, and there, if you have questions, yeah. If none of these times work, we can try to figure something else out. Also, like, I'm hoping that we can talk about the technical stuff here too. So, and we have projects here too.
Just for like the transfers, like this is my personal stance. That's really recommend that they like posting the announcements of Jeff Hanson's status course. That's what helped me pass it last semester.
Yeah. So I mean, I think I've said it a few times.
Yeah.
So yeah.
Sorry.
Yeah.
Okay.
So that I agree. I agree. That's a good resource. Okay.
Have a great day. Thank you
Okay.
so much.
Thanks. Yes.
So I was enrolled in this class until
Okay.
like before. So on my
Until
Canvas page it's
before.
like not loaded in yet.
Okay.
I did it very recently. I enrolled in this class.
Okay. So
Because I was waiting to drop a class, so I just had to enroll in this one.
Okay.
So my credits wouldn't.
that's fine. Let's go ahead and so you are registered
I am now registered.
Okay. Let me just mute this so that we don't.
Did I got it right?
Yeah, I got all 6.
So you're on session 3. Okay. It is. This is force on it, pulling it up, or that force on that pulling it apart.
I don't care with the letters, they're all the same thing.
Alright, what's your other question? Okay. Okay, so this is number 6. Okay, sorry. Okay, so there are two, in this case, we're standpoint and rotation. There was a problem where there's no rotation. And if we use rotation, so, yeah, so what question?
Happened yesterday on the previous one. I did the same thing 8 times in a row and without changing a single thing over the last one.
Okay, so these rings, so this ring, this thing stays that way. And then we have, or actually, these 3 screens are that, right? Which is the same thing as what we had before. So you've already done the rigid part, right? Now we're going to rotate, right? So that's what we're doing. So in this case, and what we need to think about is this number, right? Our ABC. This is what we want to get. We're going to assume that this is on the left side. So delta 1 on this side, which is essentially what is delta A? We're going to say, let's just assume for now that that is larger than the displacement at C. Delta C. So delta 1 and delta 2. If, right, so if those displacements were exactly the same, then there would be no rotation, right? But they aren't. Or I mean, you could define to figure out the spring system that could be, right? But let's say that they aren't. For practical purposes, this force is a little bit to the left side, right? It's not centered, for a variety of reasons. This third one. So we have this rotation now. We have a rigid body that rotates, right? And rotation is the same no matter where you think about it, right? So if I did a with respect to horizontal, right? At C, right? That rotation is still there. If I do the rotation of looking at B as a horizontal group, it's still theta, right? Same thing at A, right? That's the amount of rotation with respect to a horizontal or vertical. And so I've got that. Rotation. So now, what we get to do is there are multiple ways to do this. One is to look at using similar triangles. The other is to use trigonometry, okay? Which is what we're doing here.
Even though it's not
Similar triangles. Okay, so that one you have to look at what is the displacement, okay, with
It's crazy. I was like, I couldn't do it basically. I was like, two negative numbers. I thought it was people add two negative numbers.
It's enough looking at my yeah, but like I'm gonna do them later.
Yeah, so. Now we know that this A to C number do not change. Right, or go together, they could change. So, triangle would be opposite.
I guarantee there's
I need a
probably,
paper weight anyway.
bro,
I need to fluff my posters out somehow.
like what's gonna be the difference between the eight edition and this? Nothing. Maybe like
Maybe they discovered something new about
Yes, yes.
space engineering.
which they ordered their scam. The scam that they give.
I'm probably just gonna find a second edition.
Right, so if you go back here, that's that one and that two.
On Amazon, right?
So now we can figure out what the delta one is.
Yeah, here,
What delta one is, what delta two is, alright?
because if you're not, you know, hitting everything you need that's important, you're out. What are you doing?
See here? And then we keep it a small little approximation.
You're gonna put
But it turns out that these are things to only rotate.
We've been saying.
So theta is the value of this line.
You getting a question?
Equal rotation.
I don't know how to access the PAV markers.
You're gonna have to find something that.
So the
EDO, you go tomorrow.
And then you go do whatever you need to do, and then you'll just be there.
yeah, so what is the displacement? Okay, so the displacement. Okay, if we go a little bit further,
Okay, so
it's
it's
equal to
get down there.
delta two, delta three, delta one.
Looking at it on that side, that is a.
Okay, so
They're both.
yeah. And as I said, actually delta two, okay, so actually delta two, delta three, delta four. Okay, so the way this is delta three is now how much is from the rotation? Just from the rotation. So delta three is how much is that stretch?
Why is it negative?
And delta two is on the right side.
Wait, why is it negative?
You see that? So if you think
That's
about
positive.
how much overall delta you have delta two come down, but then you have this
I mean,
rotate.
it's also, they're both negative.
So there's an additional.
I just can't do simple arithmetic. This is crazy.
What is the extension?
This is so wacky.
I understand that.
That's right. And rotate. So V is lower than C.
Okay, so.
Right, right. Okay. And if you really want to this one. Oh, there should be, okay, so there's, okay, there should be, yeah, there's code. So if you go to the website, section 3, right? Yeah, so go down. I see this code.
5 minutes past 7. It's longer than I need to be here.
You click on the COLA. You'll find. So this is the one you scroll over. This one is 3-2.
But to be honest, I don't know.
This one doesn't have rotation. Example 3-3. So keep going down. Example 3 has rotation. So if you go down and you run this, okay. Well, first you gotta actually. So go to the very top. And we all of it.
It's 100%
Okay, and then now running. So this brings in the poker fighters.
I mean, I did really well in science. I don't know. It's just hard to understand. There are no resources. I mean supplemental resources. I meant actual learning.
Okay, so everybody's numbers. Sorry, you're good.
I mean, I'm sorry, I feel really lost. I feel like we don't get actual lectures to learn how to approach these problems. I don't know how to study, how to be good. It's very frustrating. I mean, for this week, yeah, I watched a bunch of videos, but
Just like the first one.
the first one, I watched a bunch of it, and at a certain point, my heart the audio was so different and listen to it.
Okay, she's the first one.
No, I didn't know. But in classes, you're always a I'm sorry, if it comes out of this room, then you have to.
And if you're still frustrated, it's possible, but I can before you like freak out, like
I mean, I don't know. I mean, just, thank you so much.
so again,
I mean, I want you to get our issues and everything. Thank you so much.
So now that so from this section, like we got right MR minus V equals 0. So MR minus V next to 60, I see it. But why would I?
But you still have that because if you have a moment, you still have to apply it wherever it is. Right? So it's not like, so then we apply moments at a given location. Right? We have to, or we some moments at a given location. Right? You have to still keep in mind where a force is acting. If the force is acting at the location you specify, then it's going to just be it's just zero. It's going to be zero moment there. But if I take a screwdriver and I apply a torque a moment at the location, I'm still summing the moments. I have to count it. I have to map. Right? So moments, wherever they're acting, you have to add when you do moment. That's you have to. Okay. Forces, you have to know where they're acting relative to where you've chosen to your moment. Okay, so yeah. So you have to add that. Good. All right, did that help? All right. Question? Yes. So, so.
I mean, yes, because because there's limited distance.
Okay. Yeah. Yeah. So there are like five exams. Five exams. Yeah. 5 exam twos. And then like 4, 5, big fives. So there are a lot of books there. And then the other thing is the text. This is just you can, and so if you go on Canvas under old assignments, there's old assignments that are straight from Windows. Yeah, so that will give you extra.
Yeah, I was looking at the exams, and obviously I wouldn't be like doing it if I didn't know any of it.
Right.
So I was looking for maybe like more progression wise, like I don't need any sections.
Yeah.
Sections where you have words like progression.
Yeah, yeah. So so you can look at the text.
Okay, yeah, I think that's good.
All right, good. What your name is?
Yeah.
Okay, thanks, Jay. Okay, let's do that.
And one guy was not able to upload the attendance.
Okay, so he's sending you a message. or
No,
sending me a
this is
message.
his net ID.
So okay, so have them send an email when that happens.
Oh, he was in the class.
Yeah, so
Okay.
have them send me an email.
Okay.
So if you could contact them and just say, or yeah, just send them a message, CC me, and then we'll get it started through Canvas, preferably. Yeah.
So this is the net ID for the girl. SFC. Oh, SF213.
No, SF. What did?
Yeah, SF213.
There was a. I think this kid. I think this. Person,
He already came.
I think so. I think it was SFC. Hold on a second. How do you do search in this? There's Apple.
Oh, here it's 13 SS. Yeah.
Okay,
She's it.
that's it. Okay, so we already got it then. Yeah, so in that one,